This video is about related rates. So the main idea behind related rates is to calculate the rate at which one variable changes from the rate at which another variable is known to change. So how we do that is to write an equation that relates the two variables and differentiate it to get one equation that relates the rate we seek to the rate we know. So let's look at an example. A 10-foot ladder rests on a wall. Find the rate at which the ladder moves down the wall when the distance from the wall to the end of the ladder is 8 feet, and the rate at which the distance from the wall to the ladder changes at 4 feet per second. So this picture here, it already gives us that it's a 10-foot ladder, and it also gives us that the distance from the wall to the end of the ladder is 8 feet. So right here is 8 feet. And it also gives us the rate at which the distance from the wall to the ladder changes at 4 feet per second. So with an arrow we can show the rate is 4 feet per second. So now let's label our variables. So x, we will put the distance from the wall to the ladder on the ground, and from the top of the ladder down to the wall will be h. Now, we analyze the variables with respect to time because x and y both depend on time. So what we're trying to find is the derivative of h with respect to time. So again, what we have to do is find an equation that relates the two variables. So we instantly think of, because this is a right triangle, we think of the Pythagorean theorem. So using our variables h and x, we can write x squared plus h squared equals 10 squared, which is 100. So next we take the derivative of that with respect to time, and through using implicit differentiation, we get 2x times the derivative of x with respect to time plus 2h times the derivative of h with respect to time equals 0. So we have x, and we have the derivative of x, which is 4, but we don't have h, and we're trying to find the derivative of h. So to find h, we can again use the Pythagorean theorem, and we can figure out what h was at the time when the ladder was 8 feet from the wall. So if we plug in 8 for x, 8 squared plus h squared equals 100, we find out that h equals 6. So now we have all the variables we need to solve. So we put 8 in for x, and then the derivative of x with respect to time is 4, plus 2 times h, which is 6, times the derivative of h with respect to time equals 0. And then we get 64 plus 12 times the derivative of h with respect to time equals 0. And then just PEMDAS, and we get 12 derivative of h with respect to time equals negative 64. Divide both sides by 12, and we get the derivative of h with respect to time equals negative 5 1/3. So what this means is the height of the ladder is decreasing by 5 1/3 feet per second when the ladder is 8 feet from the wall. So our label will be negative 5 1/3 feet per second. The second example is a little trickier. So it says a conical tank with a height of 4 centimeters and a diameter of 4 centimeters is being filled with water at a rate of 1 centimeter cubed per second. What is the rate at which the height of the water is changing when the water is at a height of 2 centimeters? So we have already that the height of the cone is 4 centimeters and the height of the water is 2 centimeters. And we know that the rate at which water is entering the tank is 1 centimeter cubed per second. And it's cubed because it's a volume. We also know that the diameter is 4 centimeters. So, 4 centimeters. So now that we have that, we need to think of an equation that relates the two variables we have. And when we saw conical tank, we, automatically go to the volume of a cone equation, which is V equals 1/3 pi r squared h. So we have h, which is 2 centimeters, but we don't have r. But we do have the diameter is 4 centimeters. So through that, we can figure out that the radius will always be 1/2 of the height of the cone. So the radius is always half the height. So now let's put that in the original equation, V equals 1/3 pi times half the height times h. So when we simplify this, we get V equals pi times h cubed over 12. And then we need to take the derivative of this with respect to time, because again the variables depend on time. So the derivative with respect to time, and using implicit differentiation again, we get the derivative of the volume with respect to time equals pi fourths h squared times the derivative of h with respect to time. So now we have all of our variables and we have our equation. We can just plug in what we found. So we know that the volume is changing at 1 centimeter per second. So 1 equals pi fourth, and then we know that h is 2 centimeters. So times 2 squared times dh dt, which is what we are trying to find. So simplifying that, we get 1 equals pi times the derivative of h with respect to time. And then divide by pi on both sides, we get the rate of change of the height with respect to time is 1 over pi, and then to label it correctly, it would be centimeters per second, because it is a rate at which a variable is changing. So to sum it up, when the water is at a height of 2 centimeters, the height is changing at a rate of 1 over pi centimeters per second. And that is related rates.